Now we need to talk about the properties of liquids and the kinetic molecular theory. Remember those motion of the particles. So the way we think about particles in a liquid is that those particles are close together but have only enough energy to move over and around each other. So their attractive forces are still in play. So if we look at our particle model, here is what a liquid would look like. So particles still really, really close together, but they can move over and around each other. And that also gives them the ability to flow. So nature of liquids, from your middle school definition, they have that definite volume, but no definite shape. They will take the shape of any container, but 50 milliliters in one container is 50 milliliters in another container. They have relatively high density. Density is mass per unit of volume. So since the particles are close together, there's a lot of mass in any area of volume. Liquids are only about 10% less dense than their solid counterparts. Water is an exception. It is actually it's most dense at 4 degrees C, so just over its melting point. And it gives it a lot of its special properties. Liquids are relatively incompressible. So that's because the particles are really close together, so there's no space to get rid of like there are in gases. Liquids also have the ability to diffuse. Any liquid will gradually diffuse throughout any other liquid in which it can dissolve. Diffusion is slower in liquids than in gases. Increasing the temperature increases diffusion. So I have a little video to show you that, and it does a nice job.
Place 1 drop of food coloring into a petri dish with water. This is to show diffusion in action. With diffusion, the particles of food coloring move from an area of higher concentration to an area of lower concentration over time. In the beaker to the left is hot tap water, and the beaker on the right is cold tap water. You can see how temperature affects the rate of diffusion. With higher temperatures, the rate of diffusion is higher, and lower temperatures, the rate of diffusion is lower.
All right. So what we have there talks about that ability to diffuse, and you did see that increasing temperature increases diffusion, and that's because the molecules are already moving around. So you have like your own little molecular mixer. All right. And liquids have surface tension, some more than others. So that results from attractive forces, those intermolecular forces that we talked about. Increasing attraction, so the more attractive forces, or the stronger their attractive forces, the stronger their surface tension. Water has hydrogen bonds, which are the strongest intermolecular force. So it has really high surface tension. It is what allows those water bugs to walk on top of the water. So you can see here, this right here, you see the water bending. It is using the surface tension of water to balance out its mass. Now, what's happening is these forces of attraction. Remember, water molecules are polar, and so they're going to have that hydrogen bonding, so they're going to be attracted to each other. Now, they're attracted to each other on all sides within the liquid. But at the surface of the liquid, there isn't liquid over here. So they're only attracted on these sides here that aren't in contact, or that are in contact with other molecules. So these forces right here are a bit stronger, and that gives it that surface tension. Here's another one talking about why water droplets are spherical, and that's because of their hydrogen bonding and that surface tension. Now, we can also use this idea of surface tension and the attraction of water molecules to other things for capillary action. Water, a lot of times you'll see this in blood, especially if you have to give blood for certain tests. We will use capillary action. It's like testing your blood for sugar content if you have diabetes or have to deal with that, or have ever had that sort of test. You have a droplet of blood, and then you just put the test strip right to it, and the blood seems to kind of crawl up the test strip. You may also have seen this if you spilt some water accidentally and you went to clean it up, but you just put the corner of the paper towel in there and waited a few seconds, and the water would actually crawl up the paper towel.
Jason Going, Ashley Allison, Denman, please report to Z2, Izzy Denman.
Okay, so that capillary action, that water will crawl up that paper towel until the weight of the liquid is balanced by the gravitational force. All right, now we're to talk about solids and solids in the kinetic molecular theory. So if we were to look at our particle model for a solid, particles really, really close together, and they can't move around. So it looks something like this. And the only energy they have is enough energy to vibrate. Now, nature of solids, from your middle school definition, solids have definite shape and volume, so they're not going to, those particles aren't going to move around. They do have a definite melting point. When a solid reaches its melting point, it melts. It is not a range, it is a point on the scale. And we can use that for identification purposes. If we can figure out what temperature something melts at, we can figure out what that substance is. They have high density because there's a lot of mass. Those particles are really, really close together per unit volume. And because those particles are so close together, there's no space to get rid of like there were with gases. Now, solids do have a low rate of diffusion. Notice I just said low, not no. So if you put two solids together, you will get some diffusion, but that is a very tiny amount, like on a particle level, and it's going to take a really, 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 really long time. Now, we have different types of solids. We have crystalline solids, and they have that nice ordered arrangement, have that crystalline structure. Crystalline solids have that unit cell, and that is the smallest group of particles that retain the shape of the crystal. So a popular one would be like a cubic unit cell, and you may have studied these in Earth Environmental Science. That pattern is repeated over and over and over again, and I'm not going to be able to do that three-dimensionally there, throughout the entire crystal. So we just have cube after cube after cube built upon itself. And that's what we mean by a unit cell. Binding forces in crystals. We can have ionic crystals like salt crystals. We could have covalent network like diamonds. Those are covalent network crystals. We could have metallic crystals. You saw those being formed when we did that single replacement reaction where we were precipitating silver. And we can have covalent molecular crystals like sugar crystals. That's what those are. So lots of different crystals, but they do have that regular shape, and they do have that unit cell, that shape repeated over and over again. Non-crystalline solids are also referred to as amorphous solids, so amorphous without form, so they have no specific structure. The cool thing about that is if they have no specific structure, then we can see through them. So glass is an amorphous solid, and if you've seen glass in old buildings, the glass at the bottom is thicker than the glass at the top because over time, since there is no specific structure, those molecules are allowed to flow a small amount. And so you end up with glass in old houses being thicker at the bottom than they are at the top. Plastics, the same sort of thing goes on there. Supercooled liquids still retain some of their liquid properties. We talked about those in Earth Environmental Science, talking about obsidian. That's a black igneous rock that is, it's usually described as black glass. And the reason that it is so clear on the inside is because it's usually formed when volcanoes hit water and are cooled immediately, so it doesn't give time for any crystal growth to happen. All right. I think that takes us there, yes. All right, so we need to know what an allotrope is, and you really need to know what an allotrope is. Because I'm pretty sure it's a test question. They are two or more different molecular forms of the same element in the same physical state. So, same element, same state, but they have different structures, and because they have different structures, they have different properties. So, two sames, two differents. Same element, same state, different structure, different properties. This would be, or an example that we have, are the allotropes of carbon. These three things, diamond, graphite, and buckyball, are all made out of carbon and only carbon. Buckyball is a short name for what it actually is. So all of these are made out of carbon. Now, the two that you know, a diamond and a graphite. Graphite is what you are writing with right now if you're writing in pencil. Okay, we call it pencil lead, but it is not lead at all. It is graphite, and it is made only of carbon. And a diamond is made only of carbon. Yet, these are two very, very different things, aren't they? All right, so the difference is the way that they are bonded together. A diamond has three-dimensional covalent network where it's carbon bonded to carbon bonded to carbon, and it forms that covalent network. Much, much stronger than what happens in graphite. Graphite, you have carbon bonded to other carbons, but they're like in sheets. And the sheets are just kind of stacked on top of one another, only held together by intermolecular forces. And now that works out well when you're using a pencil because it leaves part of your pencil or part of that graphite on the paper, although they are easy to break. I always break the pencil, especially out of those mechanical pencils. All right. Again, carbon, only carbon, but because they are bonded differently, they have very different properties. A buckyball is a Buckminster fullerene, is actually the longer name for that, and it is carbon 60. It is 60 carbons bonded in a sphere. We could not figure out exactly how that structure happened. We had a lot of scientists working on that, and we've gotten a carbon 60 from meteorites, and we were trying to figure out what the structure was. Some scientists were working on this, and one of the scientists just needed to take a break. So he took his lunch break and went out to a park. Now this was over in Great Britain. And the park he happened to go to had a structure on there, and it's just an artistic structure, probably about as big as this building, at least tall. And it kind of reminded me of the Epcot Center. Okay, so it's a round structure. And when he saw that structure in the park, he was like, huh, I wonder if that's how the carbon's bonded. Went back to the lab, and it worked. And so they named it Buckminster fullerene after the architect who designed the building in the park. And that's how it got its name. Now, it doesn't really have a use yet. Again, we have found it from meteorites. We know it does exist in other places other than Earth. They've tried different things. I've seen where they've tried to isolate the HIV virus by surrounding it and putting it into this buckyball, but nothing has necessarily come from that. But they're still trying to find a use for it. All right. Those are your allotropes. You need to know what it is, and you need to know that example.